Hi, everybody. Welcome to episode 31 on the podcast of Everyday Metallurgy. This episode is about laser deposition, and I have invited a very interesting guest, Arkadi Zikin. He's an expert from Switzerland working for Oerlikon, and he has taken the new boy in class within surface deposition under his arms. Laser deposition has grown over the last years to be one of the maybe most exciting. But I will stop here and let's invite Arkadi into the studio with me. Enjoy the conversation with him. See you. Hi, Arkadi.
Hello, Peter. Thanks for having me.
Yeah, welcome to the podcast on Everyday Metallurgy. Today we are going to talk about something that we have not looked at before. It's kind of you're kind of a superhero because you are my first laser man on the show. Uh, because you're working with laser deposition and laser technologies. Uh, can you tell a little about yourself and what you do?
Yes, probably it would be exaggeration to call me a laserman. I use lasers as an energy source as a technology. However, my background is more in material science, so I really love your background, which kind of microstructure with some
Yeah.
precipitations in it. So
Yes.
I feel myself also coming from that world. So saying that, I would say my life was always related to, let's say, studies in powder metallurgy. I'm Estonian, coming from a small country in North Europe, Estonia,
Hmm.
from a mixed family, having some also Russian roots, Estonian roots, many different roots. And I started my studies also in Estonia in the direction of powder metallurgy. So it was part of mechanical engineering, but with a direction to materials engineering. We don't call it material science because, as my former professor always explained to me, material science is just microstructure. Materials engineering is understanding the processes behind the microstructures because
Yeah.
you can use metals everywhere.
Hmm.
However, to understand how the technology does change properties of those metals, it's more a key to be integrated in the industry.
Yeah.
So, and that's how my journey started. More up and downs in terms like, how people study, young guys, work experiences. And I ended up somehow with luck in Austria at Tribology Center. It's AC2T, quite famous place for those who are aware of wear resistance, tribological
Hmm.
applications. And I had the luck to do a dual studies PhD at Vienna University of Technology under Professor Danninger. Great
Hmm.
guy. I really
Yeah.
learned a lot from him. And
Yeah.
also Professor Husainova. She actually made my current life possible. I'm thankful to all those guys and also to ACT2 colleagues to be able to get there where I am now, educating me, putting efforts that I also believe in myself because it's important that young PhDs, students, will grow
Mm.
to some experts. Yeah,
Yeah.
let's call it like this. And considering tribology, I started it with powder metallurgy, and then I realized powder is just a material which you proceed. So
Mm.
there should be a technology behind. That's how I ended up by plasma transfer arc, which is, let's say, a technology still quite well established in industry, and
Mm.
then moved to that time, I would say, a novel technology called laser cladding, which were using instead of plasma, laser as an
Mm.
energy source to build the same quality, also not same quality, same properties coatings, but with a higher quality. That's how I
Yeah.
ended up with lasers. And it's now already over 15 years that I'm working in the field.
Yeah.
Must be honest with you, uh, last 5 years, more even, I changed to a dark side. That's
Yeah.
how engineers call it, yeah. And went to management and to leadership
Yeah.
position. Various reasons for that. But my motto was always, if I see talents and technical talents and nerds, and for me, nerd is more a compliment rather, let's say, hey, you're a nerd. Yes, because I love what I do and do it with a passion, and I want
Yeah.
to drive technologies. And those people usually don't want to be disrupted by management tasks.
Hmm.
Hours booking, project management, cost calculations, talking to customers about every penny you need to save on certain projects, it's a headache. You want to work for technical challenges, you want to be motivated in terms of solving technical issues. And that's what I realized. Okay, I'm not a bad engineer, but probably not the best. And I could be this bridge between management, helping technical people maintain on a technical level, and myself sacrifice an engineer in me and cover their back. That's
Yeah.
how we started to build a center of competence. And currently, we are, or we might be considered, as one of the most known established centers of competence for technology within industry in Europe.
Mm.
It's a very important remark in Europe.
Yeah.
People know us, we know people, we have very good projects, we have grown 2.5 times, continue to grow. And I believe industry also recognize what's our advantage and potential in
Mm.
terms to make technology, help them to solve their issues and bring everybody money. Because at the end of the day in industry, it's all about money.
Yeah. So now over the next half hour or so, I'll put you in a bubble where you don't need to think about any kind of management. Now we can just focus on the technology.
Let's do it.
That must be a gift for you.
Yeah, I miss. I mean, I do lecturing. Sometimes I'm invited to universities, sometimes to conferences. I do it always with pleasure because you can't entirely kill a technical background in yourself. And it's also not required. By killing it, I would probably say more that you need to build a trust to technical people you lead, and you need to make them responsible for the technical challenges. Because what for educate an engineer or even senior engineer if you make all the decisions, technical decisions for him? In that case, you don't need an engineer. Or how would you see that?
I fully agree. In fact, I took the step. I've been manager for too many years, and lost the connection to my theoretical background. So my mothership, my metallurgical competences, they started to vanish, or to be not that strong. So people started stopping asking me for help,
Yeah.
and that was a warning. Peter, come back! I'm here. Metallurgy was calling for me. Uh, so this is also one of the reasons why I personally love to make this podcast, because here I meet all the happy nerds that are so much in love with their technology and their materials that I just glow inside as well.
Yeah, it's a good motivation. I had more or less similar reasons of doing that, also explaining technologies with simple words to people around, because I understood at certain point, especially if you integrate new technologies to industry, there are a bunch of questions coming from management, from customers, and they repeat and repeat each other and never try to understand. So why
Mm,
not to try and find a way to simplify the language, introduce a word of technologies and explain how they can benefit from us. So in the best case, if you talk to a financial guy, you don't say a word technology. You say money making technical method or whatever you call it. Yeah.
mm,
So translate it to numbers, put it in an Excel sheet, and he understands it.
mm. Yeah. But should we jump into the real technical part?
Yeah, let's go there.
Yeah, because I would love to talk about the laser deposition technology.
Yeah.
Can you bring some light on how it works and where it came from? Because you said it's one of the new technologies. What was before that? What did it substitute when laser deposition came into the world?
If we look on the roots of technology, we will end up in a processes called overlaying, hard facing. And those processes were initially coming from a welding process. So as soon as welding was developed, smart people came to an idea. Welding is typically used to join two metal pieces together.
Mm.
Then you use a filler material to be able to join them together,
Yeah.
or you can do it without a filler material using laser energy sources, which helps, for example, for thin metal sheets, avoid any filler material, which might have an impact on mechanical properties or metallurgical properties. Yeah.
Mm.
Not going into theoretical details, once per person said, what if I put on my base material, which might be a functional part,
Mm.
something with different properties using the same welding technology and the filler material to
Mm.
protect it from harsh environment,
Yeah.
abrasion. Let's take a very simple example from agriculture. Yeah. Typically, if you work in the field, you have your tractor driving there, you interact
Mm.
with the ground. And in the ground, quite commonly, you can have some obstacles, stones, sand
Mm.
particles. If your instrument interacts with it, we call tribological effect of impact or abrasive or
Mm.
combination of those wear mechanisms. So it burns your instrument or working body, and that means you cannot work in the field anymore.
Mm.
So what can I do? I can replace this piece, or I can to protect my existing piece of instrument or tool, which help me to work longer, to not stop the process and have so-called maintenance waiting for spare parts arrive time.
Mm.
They started to do it with a standard welding approach. Yeah, so you took a wire
Mm.
or electrode using
Yeah.
micmac, and then you end up with something which covers the surface overlaying.
Mm.
With the time, of course, as we understood the welding processes more and more, the quality has rapidly increased. You were thinking about, okay, why not only to protect harsh abrasive environment products, but also why not to, from beginning, when I produce a new part, think about cost saving. And by
Mm.
cost saving, I mean, for example, okay, I produce a part from less expensive steel and only on those areas which are suffering from any type of environment around, wear, corrosion, I
Mm.
can partially protect with certain coating on top. And more it was developing, the people realized sometimes it's not enough just to put a coating on top, because in the conventional welding processes, it's very hard to control a heat input. So if we put a heat to a component,
Mm.
we can overheat it, we can distort it, there might be
Yeah.
cracking, and so on.
Mm-hmm.
That's how people said, okay, let's look further. First, what happened, it was plasma, so process called PTA, plasma transfer arc. There was
Mm-hmm.
tungsten and inert gas processes, many different various processes. We don't need to go deep dive. And one day people said, look, there is a laser as an energy source.
Mm.
It's expensive, but it's the best way how I can throw a heat input within a small spot size. I can show you now, for example, just a very simple slide, which gives you an idea.
Mm.
Let me know when the screen is occurring. Display settings I need to change.
Yeah.
So, okay. So what is happening in laser? If we use laser as an energy source, we
Mm.
focus it with help of certain optical components, because laser is just a box. You have some fibers which bring you a laser beam to a surface. You can define dimensions. Typically, it's a circular
Mm.
spot,
Yeah.
and you can define the diameter of it or shape
Mm-hmm.
of it. So
Yeah.
means I
Okay.
know exactly that within a certain shape, which I put with my mirrors, I have an energy input. You can go in further with monitoring and temperature measurement. I can even measure temperature within this, let's say, spot. Then I can introduce a filler material in terms of powder or wire to this area. And then I build a melting bath, which interacts with my substrate material in a very minimum way. So it means we extremely reduce heat affected zones, we have less impact on substrate, and we do also minimize distortion by still maintaining a metallurgical bonding. So biggest advantage of welding, it is a metallurgical bonding. However, if we compare laser to classical MIG, MAG, and even PTA processes, the core advantage is dilution. I don't know, Peter, if you know what is dilution.
Yeah, it's the mix between the substrate and the powder you add. So typically in a welding, you have like 50%. It's typically 50-50
Correct.
mix.
Yeah. So basically, with the simple words, if I put a very expensive material on a top of a cheap milled steel, and it's 50-50 mixturing, and means in first layer only 50% of my material properties remain, and 50% will go to substrate, and also 50% of substrate gonna penetrate in my let's say coating. That means I need to build multiply layers till I get purified coating. But as we also know, if we put multiply layers, there might be more heat input, and you can cause other problems like thermal shock, cracks propagation, and so on, depending, of course, on your case. With laser, by energy input control, we simplify the system and say, even with thinly, and thinly I mean 100 microns layers, we are able to protect the surface of your materials. So at the end of the day, you can save costs, also for post-machining, because your surface after laser cladding looks filigrane. And this is also an important topic. One of the, let's say, drivers behind it is related, for example, to brake disc process. And I just want to show you a very beautiful video how you can see a process working. I put the brake here. Important to show you. This is a nozzle which from one side feeds a powder to the surface. What you see here is nothing else than a powder flow to the surface.
Okay.
Laser beam comes in the middle from a nozzle to the surface as well. This is this orange area here, because laser beam is not visible with eyes in normal environment, because we work with infrared lasers.
Yeah. So the powder is it's forced. It's not a free fall. It's injected with a gas, with a carrier gas.
Correct. So
Is
typically
it?
we use feeders which transport with the argon as a carry gas powder to the surface. But in differentiation, I know you have a HVF background. In HVF, you accelerate particles with maximum speed to surface because you want to have a high kinetic energy. In that case, it's opposite. We want to have as much as less possible powder kinetic energy, because we want them not to jump away from a melting path, we want to stay with them. And this is a second advantage of laser cladding. If we talk about deposition efficiency, which is with simple words, how much percentage of my powder which I put to the surface maintains within my coating. And we talk nowadays about 90 to 95%.
Yeah, that's pretty high. In HVOF, if we are above 50, it's a good day.
Yeah. Okay, there are some plasma processes where are below 30, and there also for laser you can have lower deposition efficiency. It's always depending what is your task, but for the normal applications, it is the case. And it's also very important to see that if you look on the process, the heat input is extremely local. So also the part, if you would do it with PTA or any other process, all the part would be already red. So your heat input is extreme high compared to laser cladding, where it's very local. There's not much of powder going out. So there are a lot of technological advantages which help us, let's say, to talk about, I call it a king of all deposition hard-facing processes, still having a background of being a welding process. If we go further, and advantages in development in laser has brought us to the understanding that laser beam can be transferred to any type of geometry. So we can work in internal diameter, so means there are some tools which enable to go inside the pipes of minimum diameter of 25 millimeters. So we talk about €1 coin, where I can go inside and cover the area. We talk about also so-called additive manufacturing, which in word of laser cladding we call LMD, laser metal deposition, or DD, directed energy deposition. And it's nothing else than we do multiply layer depositions to build complex structures and complex shapes. Yeah, they can be in the free forms, they might be with special features on top, and so on. I just give you an idea what we do at my company in Oerlikon, where we work under brand Metco Joining and Cladding. We use lasers and energy source for a bunch of different applications. We are not really dependent from one product or product group. And if there is a need in oil and gas, power generation, automotive industry, we even build the rocket components using this technology. And that's what,
I think the rocket exhaust from the Ariane 5 rocket is made with the DD.
I can't tell the details on this because this is a property of ESA, Ariane, and other suppliers. But what we can talk honestly about, and this is what I personally extremely proud of as a technology passionate guy. You know, SpaceX has introduced the third generation of engines, Raptor 3. And they say that it has over 80% of additive manufactured components. If we talk about over 80% manufactured components with additive, you can be sure there are also DD or laser cladding components included.
Absolutely, yeah.
We do our work. Unfortunately, I cannot share any results, but we are doing already 5 years, not a research, but I would say with a customer together, process qualification, and also to my knowledge, we are one of the advanced manufacturing centers exactly for this type of complex questions.
Arkadi, you said that you are able to control or measure the temperature on the deposition quite accurately. I've been working a lot with high temperature processing, and I have learned that one of the most difficult thing in the world, even more difficult than to understand your wife, is to measure temperature when radiation is dominating. So how do you measure? Do you use IR
Yes,
measurement?
one of possible. There are many different methods. And one of them, like they're used pyrometers. They have various methods how they work. They can work also within your laser beam together. So you have more or less on a similar wavelength a camera installed with also a spot laser which measures directly in melting path. Radiation, to my knowledge, is not the main challenge. I'm not an expert on sensors and measurement methods. I have even an extremely experienced guy who works in my team who is doing this. However, what I know from my experience, practical experience, the challenge is the stability of your measure signal, because if you work with powder particles, they permanently flow in your melting bath. They have various alloying elements inside, which makes your temperature measurement jump extremely. So the challenge here is how I can work with information I get out of my measurement to control the process. And I know a couple of companies in Europe who already have industrial base for many materials, let's say qualified setup to do so. So it's completely pyrometer controlled. There are still many discussions, and this is never-ending story when I meet old school experts for laser cladding. And let's say our society is quite small. Everybody knows each other, and you know all the experts. And many of them are like my age, beginning of 40s, so it's young technology from that perspective. And when we exchange by drinking beer, there's always a topic coming out. Are you sure we can use artificial intelligence? Are you sure we can measure? And I try and I have the same discussions with my senior engineers all the time. And let's be honest, I personally believe in that. I personally believe that this can be implemented in process and can simplify the whole chain. It's just a matter of data collection. It's a matter of proper way of measurement and time investing to analyze this data and learn. With all the progress we see on I believe there much more freedom coming to us. So it will also change the full understanding of many technologies perspective in the near future. My personal gut feeling.
Yeah, because my experiences are when you measure on a surface, you always have to calibrate against what is that? That is called dark black.
Exactly, yeah. Black matters.
But you never have dark black.
We
It
do.
always has a color. It always has some roughness to the surface that also influence on the surface area and the irradiation efficiency. So calibration can be, or you can measure within plus minus 200 degrees.
Standard pyrometers nowadays also offer so-called calibration device, a small furnace with a dark black spot there inside, which you can heat to temperatures which you want to use in your pyrometer. So theoretically we can use it, and this is not a new technology. And then, I mean, like, I will be very honest with you, and this is what I also had to cure, even being a PhD. When you move to industry, you have to kill a scientist in yourself. Before you kill an engineer, going to management, you kill a scientist in yourself. Because scientists would question everything and say, it has to be perfect. I need to understand fundamentals and theory behind. As a pragmatic person responsible for results in industry, I need to have enough. That means if for my process, I don't recognize a high impact on microstructure, I get more or less similar properties out, even having plus minus 15, 20 Celsius degree temperature difference in my measurement signal. As a scientist, it would be a large mistake to ignore it. As an engineer, I have enough proof with laboratories that my microstructure is sufficiently enough good to deliver me wear protection results. I have no other defects within my microstructure, but it helps me to simplify my measurement methods, and this is enough. So basically, certain calibration, it would not stay mistake, it's the wrong word, deviation, it's acceptable. Of course, plus minus 200 Celsius, no way. But an advantage of laser, what we see, within 20 Celsius degree, we are able to get the signal, which we, of course, carefully saying, because I know some people listen us and they say, Arkadi, again, you probably not telling the whole truth. It strongly depends on substrate material, and strongly depends on a filler material you put, and strongly depends on pyrometers you use. However, there is also a second method, which says you can measure not only a melting bath temperature, you can also measure a melting bath dynamics. What does it mean? You basically have a camera which shows how your melting bath profile changes, because if you get hotter, the length of melting bath is grower. If you get colder, it's an opposite. And then you can also define certain geometry and size, ellipse, whatever, and then you have two methods. So basically what we're doing quite commonly, we combine as much as possible different measurement methods, and we try to find synergy between all of them to find our equation or formula, how we define the process to be stable. This is extremely valid as soon as you start to build large-scale 3D components. Because there, if you have millions of layers you have to deposit, you need weeks of time to finish your component. It would be really pity when you have somewhere mistakes which you cannot identify. So in that case, a measurement methods to be sure that each individual layer has some data collected is mandatory, especially working in many different high quality requirement areas.
Yeah, I made an interview with a guy from Aalborg University some month ago on laser forming. And when you laser form, you heat up your metal structure, and then it bends because it's hot on one side and cold on the other. And if you control the heat input, you are able to bend it in structures that you wish.
Yeah, I saw that interview. Quite
Yeah,
impressive.
but he also wanted to be able to measure the temperature with an IR camera.
Yeah.
But when you go with your laser over and over in the same spot, you change the color on your. They worked with stainless steel, and that meant that the irradiation of the steel changed, and therefore you had to recalibrate on the
Hmm.
run your instrument, and you cannot calibrate on the run. So therefore, well, when they started to measure, they might be within plus minus 20, but at the end of the run, it was plus minus 200.
Yeah, that's quite a lot. However, what might help there, it's a
Mm,
prediction method. So again,
mm,
that's what surprised me a lot. If we think about leadership and management, they also use quite a lot of tools which work on the way of a prediction methods.
mm,
So predict a behavior of your employees, predict how your decisions can impact on your future and so on. Yeah. But at the end of the day, it's all about some mathematical and psychological approaches.
mm,
It's also here in the process. Sometimes you might predict and then you test it. And
mm.
then during the test, you might find out that your prediction works or not. And then you can improve or say, okay, that's not the right approach. So I like the saying, which some of my engineers also uh, say quite commonly, fail till you nail.
Yeah.
Yeah. So thinking out of borders, this is what we try in our center of competence to put as a core value. You know, we
Mm,
all love this marketing stories from large companies like Tesla or Apple.
mm,
Like, and there's a famous Apple employees branding interview where they say, we don't think about problem out of box or out of borders because we don't consider problem to have box or like say so we just
mm,
free to decide and become an expert of whatever we do. I
mm.
like it, even if it's more sound like a marketing stuff, but it's really true. If, as long as you can get a mindset, I want to learn and solve it, even if at the first it sounds not really feasible, you might be surprised what type of results you get. I'll be
Mm.
honest with you, my most successful project within now our group was done by a mistake in pathos measurement, where we, due to some reason, by calculating between weight percent of some ceramic phases within the matrix,
Mm.
changed between volume to weight, and
Ah,
suddenly realized that the amount of ceramic phases was twice as it was planned, and
yeah.
results were impressive. So because
Okay.
our mindset was set like with this amount of ceramic phases inside our coating, we will definitely get cracking, we will definitely get other
Yeah.
mistakes. Let's not even try. Then
Hmm.
by this accident, we make a cross section, and let's be honest, first our reaction is, what is that? How is it
Yeah.
possible? Yeah. Like, and
Yeah.
then you start to analyze and you find out and say, wow. And now it's actually an industrialized solution which is established. And now I also myself believe that there is nothing impossible.
Aha. Yeah. Yeah. That's a good way of doing it.
Yeah, sometimes mistakes help.
Yeah. If we jump back to the laser,
Yeah.
um, what level of power are you typically running, and what is possible? I know they are now developing lasers on 10, 20, even more kilowatt.
Yeah, I mean, like if you look the news, they use already in military, like to kind of drone protection systems. They work with 100+ kilowatt lasers, yeah,
Yeah.
which is impressive. Yeah, so there's like a real Star Wars blade of a high dimension going out from somewhere
Yeah.
and killing your drones. Yeah, fun enough. Uh, I will be honest with you. There is a differentiation in processes. What is offered on the market? What is now currently on a scientific level, and what most of the people still use
Mm.
commercially. And the market is quite strongly moving into direction up to 20 kilowatts commercial use. So you saw as an example brake discs.
Yeah.
Why brake discs with laser cladding? Simple fact, you can deposit directly on cast iron, which is typically from metallurgical perspective impossible because you have graphite lamellas. It's not weldable. Let's be very honest.
You cannot weld it. Or you can weld it and get a lot of cracks.
Correct. But we prove that with this technology, due to smart approach, you are able to cover the brake disc within, I would say carefully, 20 to 30 seconds, depending on the brake disc size, and get a coating without any cracks inside. That's impressive. And the surface roughness so low that the post-machining of 50 microns, it's completely enough to get a very beautiful surface quality. That's where we work also a lot and even develop materials at Oerlikon, because this is extreme mark changer, which I would consider to be the highest pusher within the last 5 years, which made our technology jump extremely from being a scientific or extremely, I would say, niche product to a technology which market is already now not less than the market for thermal spraying.
So this brake disc, if I look at my brake disc in the car, it wears and it gets smaller and smaller. But the technology you were talking about, you said 15 microns?
Let me go out from a camera and come back with an example. So I have one brake disc here with me. It's on my desk always, with a laser cladding coating after post-grinding, post-machining. What is the motivation to put on brake disc an additional process? It's all driven by the new Euro 7 norm, which says or declares the fine dust emission should be reduced. It's not commonly known fact for many people that 30% or above 30% of fine dust coming from the vehicle is coming from a combination of brake disc and brake pad. Probably, Peter, you also marked two things which happens to a disc. First of all, if you drive a lot, especially on highway, and you have to brake a lot, suddenly you realize that your colored discs are all black.
So because the dust just covers it. Yeah, that's right.
Exactly. So it's a dust covers. When I was young, I was always thinking, damn, are those streets so dirty that my disc gets so dark colored? No, it's because of wear of cast iron on the surface of your disc and the wear of the pad. This all causes fine dust particles which harm our health. And you know what? I would never live close to railway station, because if train is braking, can you imagine how much fine dust is coming out from there? People not talk about this much.
That's even worse.
That's, of course, the disc like 500 to 600 millimeter diameter. Of course, they have different braking systems, but the classical trains do also use brake disc and brake pad combinations. And so they also use cast iron discs. So what's the difference? And that's how people started to look on methods how we can protect the discs by not causing a lot of cost increase and at the same time having an advantage. And I have not mentioned second advantage. Second advantage is very simple. If you don't drive your car for a week and it stays outside, you live in a Scandinavian country, so you have a lot of salt in air because of Baltic Sea or North Sea, depends where you live. It gets all rusty.
It does.
So, and if you drive an expensive car like Mercedes or BMW, whatever,
you don't really afford that.
Okay, Volvo, still a very good car. You'll not get really happy because of the fact that your disc get dusty. It's just an orange color effect, but you say, damn, I invest so bunch of money in a car, and then 1 week later, just because it stays outside, it's dusty. It's cast iron. It just reacts. It oxidizes. You cannot avoid it. So
I have it even worse. I'm driving an electrical car. And in an electrical car, you don't really brake with your brake disc. You brake with your motor. And
correct.
Therefore, my brakes, they are worn out due to rust. So when I go to my mechanic guy, he has exchanged my brake discs because they were rusty and not because they were worn out.
Crazy, yeah?
Yeah.
And nobody's talking about this. We talk about e-mobility being a key for a healthy environment, but nobody has really realized what does it really mean and what, let's say, bypass effects we can get by changing from a standard vehicles to electric vehicles. I fully support the idea that it's an innovation and progress, and e-mobility will be a future. However, I would also say that from a technological perspective, there's still many more challenges which we still probably even don't know, which will occur and have impact on our daily lives in terms like electricity costs, electricity requirements, wastage of batteries, what we're gonna
Yeah.
do with them, and brake discs. Yeah.
Yeah.
So
So what have you done with these brake discs? They live forever.
no,
You
no,
can
no, no,
bring
no,
them
no.
from car to car. Or
No. So what was the challenge? We said automotive approached a couple of companies in Europe, first on an R&D stage, and said, guys, what can you do for us? They tried different technologies, starting with HVF, and actually we were one of the first to do HVF for brake discs. One of our materials was officially qualified for Porsche, and for several years, premium class Porsche models were having a thermospray coating on it called iDisc and offered them commercially. We were a
Yeah.
powder supplier for this application.
Yeah.
Now
What
Porsche is
material
also
was it?
moving tungsten carbide special coating. So yeah,
Okay. And
only
then
100
diamond grinded?
micron. Yeah,
Yep.
yeah. It was
Wow.
called Premium Pack Solution by Porsche. I don't have to mention that 4 disc price was probably more expensive than an average car, which you
Yeah.
can afford.
Yeah.
Yeah. But anyway, yeah, Porsche drivers were quite proud of it. But the wear resistance was extremely high. Yeah. So you basically would not need to change discs on this car.
Yeah.
However, it was also quite expensive. So thermospray technology had a couple of great solutions. However, when they realized how expensive it would be per disc,
Yeah.
they said, there is something more cheap. And that's how laser cladding came to a game where we found, I mean, like we, not necessarily me, but those people who work in a laser world, a
Yeah.
solution which says with a high-speed cladding, we can cover the surface within 20 seconds. That means our processing costs are not so high. We
Yeah.
can deposit with 95% material deposition, see a material there. So it means our material consumption rate is also pretty high, and the post-machining demand is only 50 microns. So within the full 1 minute, I just say more or less that you get a feeling, but not going some technical details out. Within a minute, you get a full brake disc ready. So
Yeah.
basically, automotive companies pay only for a minute. Of course, there's investments and so on. The processes are running, but you need to fulfill Euro 7 norm. Does it improve your wear resistance? Definitely does. Do we use carbide coatings as we used for Porsche? No, we don't. So, however, the materials which are qualified there, they all have survived in salt spray test over 1,000 hours. That
Wow.
means we talk about something which is highly corrosive protective. So this dust, and especially for e-vehicles, or not dust, sorry, corrosion is not an issue. And I'm quite excited about when this will be really in serial productions, because I would definitely, first as I would do, I would change my car brake disc to one of the deposited using
Yeah.
Oerlikon materials and Oerlikon technologies. This is what
Yeah.
when we come back to passion,
Yeah.
it's what make us extremely proud that we are part of something which is changing the world in a better direction.
Yeah. Can you disclose what metal you put on top of it?
Currently, there are several combinations. We have developed our own materials, so we invest a lot of energy and time on also to develop materials for technologies, for applications, having special properties exactly to be used in this so-called high-speed cladding process, had and at the same time still meet requirements and quite harsh requirements in terms of price. So we have developed a ferritic alloy. There is an official Metco brake brand name behind it, which we also have qualified for several companies who are tier one, so OEMs directly working for automotive vehicles. There are also a couple of solutions which are more wear resistant. So you can also reinforce certain serratic matrix alloys with carbides. So they reinforce them with titanium carbide. There are also titanium carbon nitride solutions available. So there are a bunch of companies working to offer their solution to automotive companies and say our solution is the best. At the end of the day, for me, it's not a matter and question if your wear resistance will be factor 2.5 or factor 3 times higher. It's also not the matter if your material will be 1 or 2 euros more expensive than other competitors. It's more a matter if we can convince automotive industry that in this extremely huge volume, because we talk about million brake discs, you get same quality and repeatability using one another powder and getting one and the same result all the time. So from Oerlikon side, and this is what I'm actually quite proud of, we put the most effort to guarantee that our quality of material we supply, the way we developed it, will keep the repeatability and trust which help us to win the customers, because let's be very honest, we are not the most cheapest on the market.
There are some expensive suppliers on that market.
Oh, there for sure. I mean, like, we're also not the most expensive ones, yeah. So it should be, but we would be considered as a, let's say, more a high-end, high-tech supplier, which gives you a lot of trust, which gives you a lot of safety factor, but which makes you also to be willing to pay a little bit more than you do. It's also the same if you buy, I would say, a furniture at your home, you go to IKEA, or you go to some kind of very small but extremely specialized handmade wooden furniture, yeah?
Yeah. Arkadi, that surface you just showed,
yeah,
was that as deposited?
No.
Or do you have to grind it afterwards?
I have a picture, also a picture. You know,
Hey, while Arkadi is looking for his component he wants to share, I'll just give some background information on these tungsten carbides that we're talking about. Because what is a tungsten carbide? A tungsten carbide is tungsten that is chemically bonded with carbon, and tungsten carbides are extremely hard. They have a hardness of almost 3,000 vigors. Diamond in that scale is around 10,000, but sand, so you find on the beach, which is pretty hard, it's only around between 900 and 1,100 vigors. So it's almost 3 times harder than sand. Very difficult to wear off. But the carbide itself, you cannot glue them together like that. So you have to have a binder system around it. And in this case, the binder is a metal binder phase. It could be chromium nickel binder, as it often is in these cases. And you can have binder phase around 20%, as low as 20%. But typically you have binder phase that takes up space around 30 or 35% of the volume. And then the remaining of the volume are these extremely hard carbides. And the carbides are the reason for a very high wear resistant, especially when we talk abrasive wear. But Arkadi is ready, so back to him.
Sure. You know, slides show something, but slides don't give you a full idea about what is happening. So with a high-speed laser cladding, the typical surface after deposition looks like this. So it's there is a roughness, but we can achieve something between RZ 20 to 50, depending on process parameters, depending on how you treat your process. So it's pretty even surface. When you, as an expert in thermospray, would probably say looks quite typical for thermospray.
Yeah, but it looks pretty flat compared to HVOF.
Correct. So if I go to a classical laser cladding, usually we have something like this.
Yeah.
So you have this, how's it called? up and down behavior because you do you do a line in laser process, and then you overlap this line. In a high-speed process, your overlapping is around 90%. So you basically almost not overlap. But due to the speed and velocity, you don't see this effect at all. But what we can do, you can also work with laser remelting, so you can even remove some roughness components from surface. We have a bunch of experience in that you get a really shiny surface out of that. For certain applications, people say, that's absolutely enough. I actually don't need a better surface quality. Yeah? So then you can completely avoid post-machining because let's be honest.
Can you do that with the same speed
yes.
as deposition? So that's 1 minute again?
Yes, for the break this surface here.
Yes.
Below 30 seconds.
30 seconds. Oh, wow.
Yeah. So that
and
you
nowhere on a grinding tool and.
Correct. So that you understand currently the depositions rate go to direction 5 square meters per hour. Considering coating thickness of, for example, 200 microns.
Yeah. That's pretty thick as well.
Yes, by one pass.
Yeah.
And if we talk about additive manufacturing, certain compositions, we are already going to direction of so-called MIG-MAC processes. So if it's known that with MIG-MAC, your wire feeding is probably 3 to 5 kilograms per hour, using nowadays lasers of 12, 15 kilowatts and also feeding the wire, you get more or less the same result out, but you have much better surface quality.
Yeah.
Yeah. Give me a second again. I'm running back and forward, but I guess it's also interesting to show.
Perfect.
Yeah. So if we talk about wire deposition, this is more or less what you can do. I would say here's 8 to 9 millimeters by one pass. So you can get pretty nice wall thicknesses. And what is important, yes, you have some roughness, but if you consider this is 3 kilograms of wire per hour, your post-machining demand compared to MIG-MAC technology is factor 5 less. So your process might be a little bit more expensive due to more expensive equipment, but I always, when we discuss with customers, they realize that we need to consider not only process cost, we need to consider final product costs. And the final product cost typically is impacted not by laser processes, impacted by post-machining. You reduce the post-machining, you get cheaper.
Yeah. Can you also, by laser deposition, build up 3D structures with internal channels or cavities?
To a certain extent. I like your question. The difference with the laser cladding, if it's directed deposition, is you always need a substrate. So you need an interaction point on your on your component, and on that you start to build. It's very simple way have you know it from plastic 3D printers. So can we build internal holes? To a certain extent, because in this case would mean we need to work overhang. Under a certain degree or angle, we can do this. To do repeatable structure of these honeycombs and things like that, this is a special case on the additive manufactured copper part without distortion, we can also do. So there is a lot of knowledge behind in terms how I do design my process. And by process, I mean also fixturing. Because if you need to build 3D parts or you have to do complex shapes, it's not only about to start a laser, put a filler material, and build something. It's also about understanding the whole process chain, how I control the process. What about the fixturing? How I might put my strategy, which surfaces I do first, how I cool down the component if it's required. And this is what probably I'm quite proud of in terms that the team which I have a privilege to lead or supervise has gained a fundamental understanding how those various technologies within the laser cladding or the portfolio we have impact your process, and how understanding them, fixturing and so on, diversifies your offering to a customer.
Yeah. You said previously you had this aha experience with the accident with the wrong mix,
Yeah.
where you had a cermet, a mix of ceramic and metal. Uh, so are you able to deposit every kind of material? Could you deposit pure ceramic, or or are you limited there?
That's a good question. So basically, in any welding technology, you need to bring metal to a molten phase.
Mm.
Otherwise, you cannot build a coating out of that. So we always need a metallic binder which has a more or less lower melting temperature, which would bind those, let's say, ceramic particles together. Um, there are a couple of also Chinese papers which pretend to say they have experience of depositing zirconium oxide or zirconium dioxide. Yeah.
Yeah,
You read those
on a
papers,
metal
you see
substrate.
on a metal substrate. You read
Yeah.
those papers, you get the feeling, okay, but
Mm.
I have never seen a full large-scale microstructure on that. Some local image,
Yeah. Hmm.
yes, but we don't know if outside this local image there are some cracks, there are porosity, and so on. Theoretically, as I told you before, everything is possible, but there are also some physicist laws, and they are applied to everything we do, and that means we also have certain limitations.
Mm.
I would say we achieved sometimes 80% of hard phases to be within the microstructure,
Of
but
volume.
volume,
Yeah.
which is already a huge number.
Yeah.
For example, we had a successful chromium carbide nickel chromium, the typical thermal spray material
Hmm.
application to a certain substrates, but also in a certain, I would say, lab scale conditions.
Mm. Yeah. But when talking pure ceramics, you could deposit that with a plasma instead, but not have this welding connection.
Yeah, but
It's
then you
just a
cannot bind it to substrate. So then again, we talk about thermospray process. So
yes,
because you would not get the metallurgical bonding, because also there
exactly.
you need
Yeah.
to somehow to have let's say processes or diffusion between your substrate and your
Yeah.
coating,
Yeah.
which is
It's more a mechanical bonding
correct.
you build
Correct.
up. Yeah. Mm.
Yeah.
Uh, then I've also seen that over the last years, and not a new process, but another process called cold spray has grown. Uh, but that is more for ductile materials, as I see it.
Yes and no. I'm not a big expert in a cold spray.
Mm.
Uh, to my knowledge, they also managed to do some less ductile materials to be deposited. I experienced cold spray also as a student, and that time everybody was talking primarily about copper materials. And that's
Yeah.
impressive what they can achieve. Really impressive. Because
Mm.
they basically can even do additive manufacturing of cold spray materials.
Yeah.
They pretend to say that those materials, those coatings or even structures are fully dense. However, I have never seen, and it's not a criticism, it's more just my gut feeling. I never seen any report saying this is fully dense. So like if you build a rocket nozzle, a small combustion chamber or whatever,
Mm.
from a copper, there's so-called pressure test. If it's done on cold spray, I never seen anybody giving advertising and saying we passed the pressure test. I can
Okay.
say if I work with copper or work with Inconel using laser cladding DED, we
Mm.
passed pressure tests.
Yeah.
I know a couple of other companies who did it with niobium, a good
Mm.
example of a refractory or high melting point material, also done completely with laser cladding and pressure test passed. Never
Mm.
seen this on cold spray. I believe cold spray has a lot of future potential. It's not a secret. They did a lot of publicity on that. They're qualified to use cold spray on BMW M series brake discs.
Okay.
High tech
Ah.
market. I maybe some cold spray experts, and probably would be great that you invite some of them, can give you more information on it. I would be really happy to listen. But to my knowledge, there are two main limiting factors of application of cold spray compared to any other processes, even two and a half. First of all, you use a lot of gas, which is, I believe, combination of argon and helium. And the gas flow you need there is like 100 times more you need in laser cladding process.
Yeah, and it's heated up. It's not really cold. It is, I think, between 500 and 800 degrees C.
Okay, it's considered cold compared to HVAC, for example,
Exactly.
and so on.
Yeah.
However, and this is also important to understand, my electricity or energy costs, even if I use 20 kilowatt laser, are way below cheaper. Knowing our European situation and how they kill us with our permanently rising energy prices, for me, it's already a killer criteria to consider a technology for a mass serial production, where the machine will be running 24 hours, except it's a niche or high-tech market as a BMW M series, because let's be honest, their brake discs are not the same price if you use for Opel. Okay, the second topic here, because I to mention,
you had also, 2.5.
Yeah, 2.5. The second reason why I see cold spray challenging, it's to our knowledge, they have not passed a density test. That means even if they deposit and they say it's 100% dense, we still don't have metallurgical bonding. So there's somehow still certain voids left. And then if you do salt spray test, it's not 100% dense.
Okay.
Yeah, that's what my understanding was. And then what they don't say, what was qualified for BMW, at least what we hear from market, and again, I mean, like, we're not involved in this process, they're using a hybrid process. So they use 2-layer coatings, and the first layer is what? Laser cladding. Exactly, to give you a bond coat protection against corrosion. But from functionality point of view, to find the right pad to give you wear resistance, I'm 100% sure, due to the fact that they're more flexible in the ceramic phase selection, cold spray technology has a significant advantage compared to laser cladding. The question is this required for this type of application? Is this worth the money you pay for it? It's a different question. And the 2.5, it's a noisy. You know, HVF is very noisy process. Laser cladding in opposite is not noisy. What I know from cold spray, it's even twice so noisy as HVF.
Wow. And I think
I might be exaggerating, like, as twice noisy, because
HVF is like a F-16 jet engine, 120, 130 decibel.
Yeah, so I would believe cold spray is not below that.
Okay, wow.
Yeah, and the laser cladding, we don't even know these ear tops. We don't use them.
Okay, yeah, that's easy then.
Yeah.
Arkadi, we are metallurgists, and I would like to dig into the deeper metallurgy at the end of our talk. So the particles you deposit, what are typical sizes of these powders?
That's a very good question, because the secret is here very simple. There are standard particle grain distribution, or PSD, particle size distribution, for processes. In conventional laser cladding, it is between, I would carefully say, depending on a supplier, starting from 45 microns being the lowest cut, going up to 150, 180 microns being the coarse powder, depending on who is doing this, what the price is. I know some companies put the range of particles wider from each other to drop the powder price, because during the automation process you get only a very small certain percentage within your required PSD, and all others you have to remelt and bring back, which extremely increases your cost. So some of them manipulate with this. At Oerlikon we have clear defined particle sizes, which makes our product again more expensive, but at the same time better quality, because you meet the PSD.
I have a story I need to tell you on that.
Go on.
Yeah, my father, he passed away some years ago, but
Huh?
he always told a story that the most expensive meal you can buy in a restaurant, that's the soup made on a tail from an ox. And the reason was that if you only take the tail, then you have to throw out the cow. And to throw out the cow is very expensive.
Yeah.
And that's the same story. If you only want to use this portion of your atomized powder with this fraction, then you have to pay the entire but you only get this.
Or you have to justify your portfolio using different deposition technologies where different PhDs can
Yeah.
benefit from synergy effects.
Hmm.
It's, I
Yeah.
guess, for any product portfolio manager, the core question. Do I have some synergies for my core product, which I want to sell to
Yeah.
customers?
Yeah. Can we find
And
somebody who want to buy a beef and not only the
for sure. Of course, if you're not in a vegetarian country, yeah.
yeah.
uh,
Yeah.
yeah, but finishing this, like answering your question, using
Mm.
for brake disc and so-called high-speed processes, we're on the fine side of the cut because due to extremely fast rotation speeds we use,
Mm.
and to melt the powder properly, we're actually working between 15 microns and 45 microns, might be to
Okay.
53.
Yeah.
The key to success here is because if you go to fine cut, there are some different physical laws start to work because smaller particles tend to have more energy to
Hmm.
connect to each other. So it
Yeah.
means they build satellites. Satellites
Yes.
have a strong impact on your flowability.
Hmm.
And if your flowability is low, you cannot bring your powders to a process.
Mm.
So the key is to, even if you have a fine cut, to have within this cut distribution the way that the satellites are not present in your powder.
Mm. Yeah, that's the difficult part of atomization.
It is.
Yeah. Yeah.
It is.
Um, then when I look at the microstructures from many other deposition technologies, these microstructures, they are splat microstructures. So you have particles, typical spherical, but when they hit, they flatten out.
This is
And
in sema spray.
yes,
Yes.
exactly. Yeah.
Because you have deformation, so you build pancakes. I love to call them as a pancakes. You
Yeah,
deform them, they put
yeah.
pancakes which stuck to each other.
Yeah, but how does the structure look when you laser deposit? Does it have crystals?
Yes, it does.
Are you able to see that it is deposited? Are there
Let
any?
let me find an image
Yeah.
which I love to show. Um, just a simple tungsten carbide microstructure. So
Yeah.
MMC, metal
Hmm.
matrix composite, and the way you get the microstructure out of it. So give me a second so I can share my screen with you again and show you how does it look. For me, also having this metallurgical background, I just love them. I mean, like to make a calendar of them, we usually
Yeah.
do it. Primarily, we do it with the technology, but sometimes we do it also with microstructure pictures. So
Mm.
now you see here a classical material. We have
Yeah.
changed the name, Metcoclad. This is multiply layer deposition of tungsten carbide spherical particles in a nickel
Okay.
self-fluxing base matrix.
Yeah.
So if you look closer, and this is most important image,
Mm.
this is so-called fused tungsten carbide. It consists of two phases, white and dark one, which
Hmm.
have a different amount of carbon inside. So it's called tungsten, double tungsten. Yeah. So I don't know how is it in
Okay.
English. As a
Yeah.
fused tungsten carbide is a proper name. What
Okay.
happens typically within? You have a dendritic nickel self-fluxing matrix. You can see it here, and
Hmm.
in
Yeah.
any conventional process, typically you melt those carbides extremely down that they actually recrystallize and build your etaphases inside the microstructure.
Yeah.
Here you see a very beautiful maintaining rounded shaped particle, which was an
Mm.
initial particles, and there is almost no diffusion zone of a tungsten carbide. So,
Mm.
which helps you to keep a carbide hardness. I will put it now white color so you can see it,
Yeah.
almost up to 3000 Vickers.
Yeah.
It's an impressive number. And there, if we look deeper, are extremely well and uniform distributed within your coating profile. And this is only 60 weight% of, which corresponds to 40 volume% of tungsten carbide within metallic matrix.
It is not possible to see on the microstructure that it is deposited. It doesn't.
It has a casting microstructure. Typically, it has a typical casting microstructure. I can probably give you an example more on a, let's say, stellite example. Yeah.
Yeah.
I have. I don't know why my PowerPoint is not working properly today, but here. So if you look on a stellite, like 21, it has typical hyperprotective structure, dendrites everywhere. So you get it from similar way to casting. The difference with laser cladding, due to low heat input and extremely rapid cooling, your microstructure is 10 to 100 times finer compared to casting. So if you see here the 40 microns and dendrites are pretty small, which gives you a possibility for many dendritic alloys like stellites end up with a higher hardness values directly after deposition. So you get better
the whole
properties.
patch effect shows here that finer particle or finer grains, you get higher hardness.
Correct. And you get also better corrosion resistance because you have much more grain boundaries. Yeah. So this is a differentiation factor what we see. And knowing that, it's also important to adapt your process because, and best example is Stellite 6. I love this example because people come to me and ask usually, oh, Stellite 6 is one of the most used materials. It's well known. But if you do micmac deposition, you never get over 38, 40 Rockwell. Yeah, which is a standard value. Then if you do PTA, you probably end up with 40, 42. I say with laser cladding, we get over 50. Yeah, so same material, just due to the heat input and slowdown or rapid cooling, your dendritic structure creates grain sizes which differentiate from each other. Even if it's same microstructure, just the only difference is fine or coarse dendrites, and this impacts your hardness and at the end of the day, wear resistance.
Yeah. Do you sometimes need to heat treat the structure afterwards?
Depending on material and requirements. What always might happen, especially working with harder materials, is that you introduce stresses. And in processes like if you do oil and gas, and you use even this, what I showed before, tungsten carbide reinforced, because this is a flagship material used in oil and gas. They insist, depending, of course, what the final application, but some steering pads, some drill bit surfaces, some stabilizers, they insist to have annealing to ensure that we get rid of stresses inside.
Yeah, because many applications, they occur at 300, 400, 500 degrees. So they want it to be annealed above that temperature.
And there's special materials. If we talk about power generation, air applications, you work with Inconels. And if you need to, like Inconel 718, as a great example, you need to have these gamma precipitations, and this what you can get only with heat treatment. So there you have special afterwards heat treatment processes to change your microstructure the way it's needed to get the precipitations inside.
Yeah, but the precipitation must be very small and very homogeneous distributed compared to casted as well.
Absolutely, and they are. Because I mean, like what we quite commonly do is repair on casted materials. I can tell you the biggest advantage is, and this is what many people still don't believe, we can do repair on a single crystal material. So it's a single crystal casted material using laser cladding and the proper approach of energy input and cooling conditions control. We have proven that we can do crack-free repair of single crystal.
Do you grow the same crystal, or
no,
do you
of course,
grow many micro?
It's called epitaxial grow, yeah? So you have grain orientation more or less in the same direction. I will lie if I tell you that it's completely epitaxial. No way. But it's more or less have a tendency to look epitaxial.
Yeah. So that must also mean that for these high temperature materials, where you have creep risks, when you have very fine precipitations compared to cast, you could run it at a little higher temperature.
Yeah. But is it used a lot? No. Primarily, laser cladding in this market is used for repair.
Okay.
There are some other reasons of doing this, because typically those substrates, single crystal is one of the examples, which is almost unweldable. They use alloy grades which are also not weldable. Like
Okay.
Inconel 738, Rene 18. There are many materials which typically are not very easy to deposit on. We have over 25 experience coming back to our history of Metco, Sulzer Metco times, where we did a lot of repair also here in Switzerland for turbine blades. This business has been completely moved out to Asia countries. Nobody almost doing blades repair in Europe, except some exceptions within large OEMs. But what we do, for example, and what we are also quite proud of, we do cubic bore nitride protection of discs, like against abradable coatings by rubbing function of a blades, where we have qualified a couple of projects in that direction. Without naming companies, we found out how we can do a very high level and high quality cubic bore nitride deposition. It's not an easy, not an easy target. Yeah.
I have a very last question.
Go on. Time is flying, unfortunately.
Yeah. Where do you see this go in the future? Now, it sounds like the brake disc has been the breakthrough to enter a high volume market. But will it continue? Will there be 10 projects like brake disc high volume, or hundreds, or is it a one-off?
You know what? Of course, we do a lot of strategic researches. And I would say that I'm well connected within this brand industry. And I told you already that the probably total market size is already reaching the thermal spray market sizes, because there are so many applications which are just popping out, which nobody had on a radar before. Brake disc was a moment for technology, but not only for market opening. What does it mean? A lot of prices for laser sources, a lot of prices for nozzles, some spare components has significantly dropped. I give you a very interesting example. When I was a young student back maybe 15, 16 years ago, to have 5 to 6 kilowatt laser, it was like wow effect. And the price of this 5 to 6 kilowatt laser, which was itself quite a high size package, heavy weight. I still have 16 years old IPG laser, which is like 2 tons weight of the laser.
Yeah.
Impressive, yeah. And it's like a box, quite high dimensions. The price was over 1 million euro. Nowadays, I have to be careful not to name the real prices, but let's be honest, I can get 6 kilowatt laser, if it's like diode laser or more or less similar quality, more or less by factor 10 cheaper. Yeah, so 1 million, 100,000. And if I go and talk to Chinese customers, they're selling prices between 3 to 5,000 euros per kilowatt.
Wow. And the size is not cubic meters, it's
laser line, which I love. This is great. People will work a lot with them. 6 kilowatt laser is this type of the box nowadays. Yeah. And this is funny because I have one 12 years old 6 kilowatt laser in our department, and we have close to it a new generation one. And you look, one is as large as me, second this small box, and they both are 6 kilowatt. Yeah. The question is where it's going, what is the development, and where is the end of this? So but I did the studies on that, and I have also very nice analysis what was the break off actually for a technology, because people forget that the break off is actually what is an important way how technology gets from this S curve to a fast, rapid growth. I give you an example. Do you do sports, Peter?
Yes.
Yes.
I'm
Do you
playing
measure
basketball.
do you measure your, like you see on my watch? It's
Yeah.
for me not a watch because I don't wear expensive Swiss watches, not because I
Mm-hmm.
don't like them.
Oh,
For me,
yeah.
this is a powerful tool.
Mm-hmm.
This measures all my life.
Mm.
Temperature, VO2, steps, everything. Yeah.
Yeah.
So, but you know that the first ones who came there was Fitbit. When Fitbit came to market, everybody says it's a bullshit. Nobody needs it. Why should I need a bracelet here
Yeah.
to measure something? After people realized what is behind, now everybody,
Yeah.
iPhone or Apple, sorry, Samsung, everybody
Mm.
has its watches. The watch market has
Yeah.
skyrocketed, and the breakpoint actually was the startup of Fitbit. Before
Mm.
that, nobody. And
Yeah.
if you look on the scale, it happened maybe 12 years ago. So before
Mm-hmm.
that time, we always forget it. There was
Yeah.
nothing. So, and
Mm-hmm.
that's also the break point for me for technology was this massive drop of the price, which actually happened
Mm.
thanks also to a break disc process. Because I love automotive people from the perspective that they're extremely price reduction driven.
Mm. Yeah.
And
That's
from
right.
technology, the technologies are great. Yeah. For people
Mm.
who have to sell lasers, it's not easy because they need to find the ways how they get the lasers constructed cheaper, cheaper, and cheaper and cheaper. Yeah. So,
Yeah.
but at the end of the day, it's a driver. So,
Mm.
where I see we mark extreme direction hard chrome replacement in many sectors of life. It's sustainability. I know many companies who do it in hydraulic rods. One of the latest, what you can find out without telling details,
Mm.
smartphones.
Yeah.
You know that the people go in smartphone housings to titanium. There are several reasons for that. But if you
Mm.
buy new iPhone generations, the housing is
Yeah.
titanium.
Okay. Mm.
Titanium is not an easy material. So basically,
Nope.
you need to take a block of this size and
Mm-hmm.
start to machine a housing. And if you open
Ah.
your smartphone, you
Yeah.
have many
Mm.
adapt features in it.
Okay.
And now you ask your question. What is one of possible ways to
Mm.
make those features in this
Mm.
area on the titanium plate possible in a very cheap conditions and fast?
Yeah. Uh-huh. You laser deposit it. Mm.
That's what you told. And this opens you
I'm
quite a lot
I'm
of
just guessing.
horizons. Yeah, but this is, can open you a lot of different
Yeah.
perspectives.
Yeah.
It might be not only this, it might be iPads, it might be
Mm.
laptops, where
Mm.
everywhere where titanium comes in questions, it might be a direction. Another
Mm.
direction, I told you 80% of components of rockets. So definitely space. ESA published recently a paper, they say we were the first to use a laser supported process to do repair of spaceship or whatever they used it
Mm.
in space.
In space.
In space.
Yeah.
So people
Mm.
start to think out of borders. So you fly, you have a robot hand or whatever, and you
Yeah.
use wire because
Mm.
powder feeding due to gravity is impossible. And with
Yeah.
wire, you just repair some
Mm-hmm.
areas, putting
Yeah.
hard facing there. So
Mm.
where's the technology going to bring us? I don't know.
Mm.
It's to some extent a niche product. Somewhere it's established. Somewhere people start to think about it. I know steel industry has a bunch of applications where laser cladding could be a benefit from them. The problem of steel industry, it's extremely laggard.
Mm.
Extremely. You have a
Yeah.
specs there used from 1970s, 80s. And
Mm.
if you don't meet the spec, they are not willing, because it's also too expensive, to change the specs.
Mm.
They still
Yeah.
use spray and fuse for many applications. Nobody's using this spray and fuse anymore, yeah, because
Mm-hmm.
technology is quite old. Right, for to have two processes where you can do it with one, like laser cladding or even standard semi spraying, but it
Mm.
is written in their specs since 40, 50 years,
Yeah.
and it's very hard to convince them.
Yeah. That's right. Uh, but something is happening, and I agree with you on the story about laser going down in price. I made an interview with an expert in material for fusion reactions, and she told that one of the that there's the ITER project with the tokamak system. That is the high runner. But then there are spin-off technologies, and one of them is to have a pellet with your material, your deuterium and tritium, and that pellet is on a little spot, and on that spot you put laser power, but we're not talking 10 or 20 kilowatt, we are talking maybe hundreds of thousands or many kilowatt. And if we just said 10 years ago, the supply of laser would be an entire football field. But today, you can put it in a big room. So it's a big difference. Just what has happened over the last 10 years.
What will be? It's like you can put like an example to the computers as well. Yeah, like transistors, their size is moving down. Same with the lasers. Yeah. So at a certain extent, where are we going to be tomorrow? Maybe we will end up with something which a laser price will be by 500 euros per kilowatt. In that case, you will be even cheaper than MIG-MAC processors, because let's be very honest, if you want to have automated process, your core costs will be for core equipment, because robotic or gantry system, if you use MIG-MAC or you use laser or you use plasma or you use thermospray, it's the same. If laser is 1 million, it has an extreme impact on your final cost. If laser is similar price to a current box for your welding process, but you get much better quality out of it, there's no doubt everybody will jump on this, because honestly saying, there's no better energy source than laser which humanity has developed so far. Maybe there will be something more carrying.
I will have a laser in my own tool shop at home, and then I will repair my own brake discs if they don't come up with it very soon.
Don't forget to write us down, Peter, and I will be happy to give you a required powder for that.
Perfect. Thank you very much.
Thank you as well.
That was the show for today, everybody. If you enjoyed it, if you liked it, if you want to share it, please feel free to do that. Share it with your friend, press like button, and follow the Everyday Metallurgy podcast on YouTube. That will help a lot to bring this to other people who might feel interest in material science. Thank you for joining, and looking forward to see you again in the next episode. Next episode will be on next generation high entropy alloys, and something is really happening within that field. So stay tuned. See you soon.